All right, so now we move into our second unit for Math 15, and we start with lesson 1 being the exponent laws of products and quotients. So right off the bat, what we want to do is we want to establish, well, when we look at exponents or when we talk about exponents, what are the elements that make up exponents here? So we always have some number which is represented by the base, and that's going to be a number, it could be a variable. In most of the cases we're going to deal with, we may have numbers and variables. So it's just a matter of the context of the problem. And then we know that exponents, well, that's going to be that little number up in the top corner, and an exponent technically can mean that we just write out an expansion of whatever number we're dealing with here, or an expansion of whatever variable. So on the right here, we see that we have a base of 2, an exponent of 4, and that means we write out the number 4 times as a product or the multiplication of those numbers. Now, as a sharp contrast, what I could do is I could go, what if I had x to the power of 3? This is instead of a number, I have a variable. I'm going to expand this as the product of this 3 times. So the exponent is just a representation of expanding out whatever you have in your base and using it as a product or the multiplication of those. Now, let's introduce some laws right away here. Some exponent laws to do with products and quotients. Well, we know just from above that the product rule, which we're going to come to realize, the product rule, or one of the rules we're going to deal with here, is the repeated multiplication of some base value with some exponent. So we're talking about this one right here. It expands out. We have whatever, n number of b's in this case, and they're all multiplied together. Another really important rule is saying, well, what if I have instead this b to the 1? Well, anything to the power of 1 is immediately just going to be itself. So we can just write a direct carbon copy of whatever it is. So let's say, for example, I had 7 to the power of 1. This would be equal to 7. And I could do that with variables or numbers or whatever it is. We then have, what if I raise something to the power of 0? Well, we get this is equal to 1. And now, if we were in a more applied proof-based course, what we could do is we could show exactly why this is equal to 1. However, for our exponent laws, we just really want to narrow in on the idea that anytime something's raised to a power of 0, it's equal to 1, no matter if it's a variable or number. So I could give you an example of maybe y to the 0. Well, y to the 0 is still 1. Or I could give you, what if I said 4 to the power of 0? Well, that's also just equal to 1. And then finally, we have our reciprocal rule, which says that anytime we deal with a negative exponent, it's going to flip the base value. Not the fraction, but the base value. And we'll get more to that in lesson 5. Now, let's work through some examples here of these exponent laws. Well, anything to the power of 0 is automatically going to be 1, no matter if it's a variable number, whatever it is. Anything to the power of 1 will just be itself, or the base value itself. If I have a fraction raised to the 0, well, both of these numbers actually get the distribution of 0, meaning that I have 2 to the 0, 3 to the 0, anything to the 0 is 1. Now this one's a little trickier because we go, okay, well, we have 5 to the 0, but what happens with this negative? The negative is not attached to the exponent 0. There's no brackets around the negative and the 5. So the 5 is the only thing that applies to the 0. This means I have a negative and 5 to the power of 0, 1. In E, the brackets are around both of these, meaning that I technically have a negative 1 raised to the power of 0 and a 5 raised to the power of 0. If everything's all together in the bracket, no matter if it's a positive or a negative number, this will always be equal to 1. Because everything's included in the brackets together. So that's something to be really careful with there. Now, if we flip over the page, here's where we formalize what we call our product rule. The product rule says that, let's look at an example and then explain. Well, if I have a squared and a3, I could expand these out. And if I add up that expansion of how many of the a's there are, well, I should have 5 total a's across the expansion here. So when I do a squared, I'll have 2 a's. When I have a3, I have a3 or 3 a's. And then when I add them together, I get this a to the 5. Now this brings us to what the product rule is. It says if I have one base and another base, meaning I have a common base, we're going to keep that same base and then add their exponents. So let's see how that applies directly in an example below. If I have b squared plus b4, well, I can say this is equal to b to the power of 2 plus 4, That's equal to b to the 6th, or b to the 6th power. If I look at part B, I have a negative 3 to the 4 times a negative 3 to the 5. That's a common base. I'm going to rewrite my common base, and then I'm going to go 4 plus 5 is equal to negative 3 to the 9th power. Now we could expand this out and we could figure out what that exact number is. However, for our case, we just want to express this as using the product rule and stop there. Now, here's something I've said tons in class. If this isn't written above, if I have something or some number, some variable, some fractional number, and there's no exponent, I want to write in a 1 there. We have 2 over 3 to the 1 plus 2 or times 2 over 3 to the 5. That means I write out the common base of 2 over 3 and I add 1 plus 5. That's going to give me 2 over 3, all in brackets because it's applied to both of these, to the 6th power. Now, what if I go to part D here and I see that I have two variables, I have an x and a y? Well, right away, I want to identify any variables that do not have an exponent. In this case, it's y. Y needs to have a 1 here. It's not 0, it's 1. If it's not written, it is definitely 1 there. Now I go x3 times x4. The common base is x. I add 3 plus 4. That gives me x to the 7th power. I look at my y's and I go, I have y2 times a y1. That's a common base. I add their exponents. 2 plus 1 is 3. Now, with our next example here, same idea, except in our exponent, now we have an x attached. It doesn't change how we approach this. I have a common base of 2. I have one exponent plus my other exponent. This means I have 2 to the power of 2x plus 4x. That's a total of 6x. Now I go to this last one here and I go, okay, I have two numbers as coefficients, 3 and 5. Do they have anything in their exponent? No, they just have 1s in their exponents because if it's not written, it's just 1 there. And so we have 3 times 5, that's going to give me 15, just purely by standard multiplication. I then have a4 times an a1. That means I have a common base of a, and I add their exponents. 4 plus 1 is 5. Then I have b1 times a b to the negative 2. That's like saying b1 plus a negative 2 or 1 minus 2. And that means I have a common base of negative 1. Now here's the thing we're going to learn very soon in this unit is when I have negative exponents, I want them in terms of positive exponents. So this means I have 15a5. And by our rule on our first page, we're actually going to flip the b value or change the base from the numerator to the denominator and make the exponent positive. And that would be our solution. So if we want to change this from a negative exponent to a positive exponent, we relocate it from the numerator to the denominator. All right, so here's where you check your understanding. This is where I would like you to practice those skills. There's lots of different examples here. There's lots of different variable examples, numbers examples. I want you to go through this, and this is going to be your homework section. Now, in contrast, we have what we call the quotient rule. So if the product rule is when we have two bases that are common and we're multiplying them and we add their exponents, then what happens when we divide two things with a common base with different exponents here? So let's consider the following example. If I have a7 over a3, well, just as we've done with product rule, we can expand this out as the 7 is representative of I have 7 a's multiplied together. Similar in my denominator, I have 3 a's being multiplied together. Well, how many are similar or how many are the same from numerator and denominator? I have 1a shared, 2a shared, 3a shared, and how many do I have left over? I have a to the 4 left over in my numerator, or 4a's to be more specific here. So when we divide the powers with a common base, we keep the base. So we have a common base, we keep the base and subtract their exponents, and that gives us what we know as the quotient rule, or two bases that are the same being divided. So let's actually see some applied examples here. I have b12 over b5. If I know I have similar base over similar base, or one base divided by another, I write the common base, and I take the exponent of the numerator, subtract the exponent of the denominator, and this gives me b to the power of 7. If I go over to part B here, the only difference is now I've written it as a horizontal line rather than a vertical line for division. So in this case, I still am subtracting the exponents. 6 minus 2, that gives me x to the power of 4. In C here, we have a common base. We always write out that common base. And we say, okay, well, it's the numerator's exponent minus the denominator's exponent. 8 minus 3, this means this is equal to negative 4 to the power of 5. We go over to D here. Now, I have a rational number here, or a fractional number written as integers, so I always need to remember, if something doesn't have a power written, let's always write 1. Because it's always a power of 1. Anything to the 1 is just itself, but for our sake, it's not going to be written, so we need to write it in there. We have 4 over 3, which is the common base, to the power of 6 minus 1, that's going to be 5. 4 over 3 to the power of 5. Now we get things a little more applied here with E, and we see x to the 7 over x squared, y to the 3 over y1, z4 over z4, or zz, whatever you want to say, different for everybody. Now, if I have this, I have x to the 7 over x squared, that's 7 minus 2, that's x to the 5th power. Y, it doesn't have a power in the denominator, so I'm going to throw it in there. Y to the 3rd power over y to the 1, that's 3 minus 1, which is squared. And then I have z4 over z4. I write out the common base. Well, 4 minus 4 is 0. Here's our first application of a 0 power. We say anything to the power of 0 is actually just 1. So we have x5 times y squared times 1. Do we really need to write that 1? Not really. We can just leave it like this, because anything times 1 is just whatever the number was there. So that is good enough for us. We go down to F. F introduces a number coefficient. When we deal with number coefficients, we always want to be thinking about, how can I reduce this as much as possible? Well, I can reduce this by saying, what does 20 and 15 both divide by? In this case, it would be 4, or in this case, it'd be 5. So I'm going to get 4 over 15 divided by 5 is 3. Now I have this scenario of A5 over A8. That's A to the 5 minus 8, which is negative 3. I have B8 over B4. That's like saying B8 minus 4, which is 4. And now I want to write this in terms of positive exponents only, because that's always how we simplify these. I have 4 b to the power of 4 over 3 a to the positive 3. If I relocate this from the numerator to the denominator, or vice versa, the denominator to the numerator, I relocate it and the power becomes positive. All right, finally, I have g here. I look at my numbers and I say, is 3 over 2 already fully reduced? It is. We can't reduce that anymore. So I'm going to write in 3 over 2. I then have m negative 1 divided by an m negative 3. This is like saying m to the power of negative 1 minus the negative 3 from the denominator. In terms of my n, I have n to the negative 4 minus a positive 3 here. This is going to simplify to make 3 over 2 to the m. Minus minus becomes negative 1 plus 3, which is 2. And n negative 4 minus 3 is n to the negative 7. My final answer, therefore, is 3 over 2. The m squared is already a positive exponent, so it stays. But I'm going to take this negative 7, or this n to the negative 7, relocate it to the denominator. Once it's relocated, it can be written with a positive exponent. All right, here's the check your understanding section. This is the part I would like you to practice.